In this video, we're going to look at a general overview of the main types of factoring problems. What can make factoring difficult is that there are lots of different types of problems, and different types of problems need to be factored using different strategies. We've discussed three main types of factoring problems. We're going to go through the different strategies for each of those three different types of problems. If the instructions say factor, step 1, check for a greatest common factor. Once you've checked for a greatest common factor, in step 2 you want to count the number of terms. For example, this problem involves 1, 2, 3 terms versus this problem, which involves 1, 2 terms. You want to count the number of terms because that will help you to decide what strategy to use. If your problem involves 2 terms, we call that a binomial. And in this box, we're going to discuss how to factor binomials. If you're factoring an expression involving 2 terms, first, of course, check for and factor out a GCF. Then you will need to decide which formula to use. If you're dealing with the difference of 2 squares, for example, if you have 2 perfect squares with a minus sign in the middle, then we use the difference of 2 squares formula to factor. The difference of 2 squares formula says if you have 2 perfect squares, we'll call those squares in general a squared and b squared, and if you have a minus sign in the middle, we factor by using the formula a minus b times a plus b. Another possibility is you might have the sum of 2 squares. For example, you might have 2 perfect squares with a plus sign in the middle. If that's the case, stop, because the sum of 2 squares cannot be factored. Of course, first check for a GCF, but once you've checked for a GCF, if you're left with the sum of 2 squares, it cannot be factored. The next possibility, if you have 2 terms, is that you might have the difference of 2 cubes. For example, we call this expression the difference of 2 cubes. X cubed is a perfect cube, and 8 is a perfect cube, and we have a minus sign in the middle. So this is the difference of 2 cubes. If you have the difference of 2 cubes, we'll represent that in general terms as a cubed minus b cubed. The formula we use to factor the difference of 2 cubes is this formula here. The last possibility is that you might have the sum of 2 cubes. An example of that would be the expression x cubed plus 8. X cubed is a perfect cube, 8 is a perfect cube, and we have a plus sign in the middle. If you have the sum of 2 cubes, we can represent that in general as a cubed plus b cubed. We factor the sum of 2 cubes using this formula here. On the next few pages, we'll go over some examples of these types of problems. The next type of factoring problem involves 3 terms. So if you're asked to factor an expression and you count that there are 3 terms, you're going to use the strategies in this green box here. Now, if you have an expression involving 3 terms, first, of course, you always check for a GCF and factor out the GCF if there is one. Then ask yourself, is the coefficient of the squared term 1? In other words, the polynomial will be of the form x squared plus bx plus c, where the coefficient of the squared term is 1. An example would be this trinomial here. And the coefficient of the x squared term is a 1. If that's the case, we need to find a pair of numbers. In general, we'll call those numbers m and n. M times n must multiply to give us the product of a times c, where a is the coefficient of the squared term, which is an implied 1, and c is the constant. And those same 2 numbers must add to give us b, where b is the coefficient of the x term. Now, if the coefficient of your squared term is a 1, once you find these 2 numbers, you can write your final answer. You just need to draw your parentheses. Since the variable here is an x, we'll put a x in the first position in each parenthesis, and then we'll put the m in one of the parentheses and the n in the other parenthesis. And if there was a GCF, you would make sure to put that out front as well. Another possibility is that you might have an expression involving 3 terms. First, of course, check for a GCF, but once you've factored out the GCF, If the coefficient of the square term is not 1, we need to follow some different steps. So we're looking here at a trinomial of this form where the coefficient of the x squared term, which we call a, is not 1. An example would be this trinomial here. After checking for a GCF, then we need to find two numbers. We'll call those numbers m and n. M times n must multiply to give us a times c, where a is the coefficient of the x squared term and c is the constant. And those same two numbers must add to give us b, where b is the coefficient of the x term. Now, when the coefficient of your squared term is 1, once you find these two numbers, you just insert them in the parentheses and you're done. When the coefficient of your squared term is not 1, after you find these two numbers, you cannot just insert them in the parentheses and be done. The process is a little bit longer. For problems where the coefficient of the squared term is not 1, after you find these two numbers, we learned 3 different methods in chapter 4.5. You can pick whichever method you prefer. We learned to factor by grouping, or instead you could use the box method, or instead you could use the factor and divide method to get to your final answer. On the next few pages, we'll review some examples of how to factor expressions involving 3 terms. The last main type of factoring problem involves expressions with 4 terms. If you're trying to factor an expression that involves 4 terms, such as this expression here, we factor by grouping. In my chapter 4.4 video, we learned to group the first 2 terms together and to group the last 2 terms together. So now that we've discussed the 3 main types of factoring problems, next we will look at some examples of the different types of factoring problems and the strategies that we use for those different types of problems. We'll go through these examples fairly quickly, so if you would like more of an introduction and in-depth review of how to factor each type of problem, please review my chapter 4.4, chapter 4.5, and chapter 4.6 videos. Let's start with this problem here. For any problem, if you're asked to factor, the first step is always to check for a greatest common factor. The greatest common factor for this problem would be 3, because 3 is the largest number that multiplies evenly into 3, 6, and 105. So since there is a greatest common factor, we need to factor out the GCF. To do that, we draw our 3 outside of parentheses, and then we think through the distributive property. What do we have to put inside the parentheses so that when we distribute the 3, we get the expression 3x squared plus 6x minus 105? Well, 3 times x squared will give us 3x squared. 3 times a positive 2x will give us our positive 6x. And if you take negative 105 divided by 3, you'll get negative 35. So 3 times negative 35 will give us negative 105. After you've factored out the GCF, step 2 is to count the number of terms, because that will tell you what strategy you're supposed to use. We have 1, 2, 3 terms. So if we look back at the first page, for problems involving 3 terms, we follow the instructions in this green box here. Now we will have to ask ourselves, is the coefficient of the squared term a 1, or is the coefficient of the squared term not 1? Now, when you're determining if the coefficient of your squared term is a 1 or not, do not look at the original problem. You want to look at the expression with the GCF factored out. So we're looking at this expression here, and we can see that the coefficient of the squared term is 1. So we have an expression involving 3 terms, and the coefficient of the squared term is 1. Therefore, we're going to follow these steps right here. And while we need to make sure to include the GCF in our final answer, we can ignore the GCF for the time being as we focus on factoring this trinomial. So first, we need to find 2 numbers that multiply to give us a times c. Now be very careful when you're determining a and c, do not look at the original problem. We're focusing on this expression here with the GCF factored out. So a is the coefficient of the x squared term, which is 1, and c is the constant, which is negative 35. So 1 times negative 35 gives us negative 35. We need those same 2 numbers to add to give us b. where b is the coefficient of the x term, which is 2 in this case. The two numbers that work are 7 and -5, because 7 times -5 gives us -35, and 7 plus -5 gives us 2. Now, if the coefficient of your square term is a 1, once you find these two numbers here, you can write your final answer. To write our final answer, we'll start by drawing our parentheses. Since this is a 1x squared, we'll put a 1x and a 1x in the first position in each parenthesis. And then we use these green numbers to fill in the blanks. We'll put a +7 in one parenthesis and a -5 in the other. And then make sure to always include the GCF in your final answer. So we'll bring down the GCF to include in our final answer. And if you'd like to check your work, you can FOIL out this expression and then multiply each term by 3, and you'll see you get the original expression. Let's try problem number 2. The first step in any factoring problem is always to check for a greatest common factor. For this particular problem, there is no greatest common factor. So now we can move on to step 2. For step 2, we need to count the number of terms, because that will help us to decide what strategy we need to use. Notice we have 2 terms, 1, 2. For problems involving 2 terms, we're going to refer to this purple box right here. Now notice, for problems involving 2 terms, there are 4 different formulas, and you will need to decide which formula to use. To help you decide, let's first decide, are we dealing with perfect squares or are we dealing with perfect cubes? 16 is a perfect square. It's not a perfect cube. And w to the 4th is also a perfect square. It's not a perfect cube. 1 can also be written as a perfect square. So both of these terms are perfect squares, and notice we have a minus sign in the middle. So it looks like we have the difference of 2 squares. We have 2 perfect squares with a minus sign in the middle. For those types of problems, we factor using this formula. We just have to determine our a and our b and then plug it into this formula. So I'm going to start by copying down the original given problem. To determine a, we want to rewrite this first term here as some quantity squared. 16 can be written as 4 squared, and w to the 4th can be written as w squared squared. Remember, when you raise an exponent to an exponent, you multiply. So 2 times 2 gives us 4. Then to determine b, we need to rewrite 1 as some quantity squared. 1 can be written as 1 squared. The quantity inside these first parentheses here in light purple is a, so a is 4w squared. The quantity inside these second parentheses here in light purple is b, so b is 1. Now that we've determined our a and our b, we just have to plug those values into our formula. The formula for the difference of 2 squares is a minus b times a plus b. So we'll plug 4w squared in for a, and we'll plug in 1 for b. And again, we'll plug 4w squared in for a, and 1 for b. Now, when you're factoring using the difference of 2 squares, be very careful. Before you complete the problem, you want to carefully examine your answer, because sometimes we have a problem within a problem. Notice here within our answer, we have the difference of 2 squares again. 4w squared is a perfect square and 1 is a perfect square. So we need to further factor this expression here, again using the difference of 2 squares formula. To factor this using the difference of 2 squares, again, we need to determine our a and our b. To determine a, we need to rewrite 4w squared as some quantity squared. To get 4, we have to square 2, and to get w squared, we have to square w. Then to determine b, we have to rewrite 1 as some quantity squared. 1 can be rewritten as 1 squared. A is the quantity inside the first parentheses, so a is 2w, and b is the quantity inside the second parentheses, so b is 1. Now, to factor this expression here, we use the formula a minus b times a plus b. So I'll start by drawing the 2 sets of parentheses. We'll put a minus sign in one parenthesis and a plus sign in the other. Then we want a minus b, so we'll take 2w minus 1. And then we want a plus b, so we'll take 2w plus 1. So we've taken this expression here, which is the difference of two squares, and we factored it here using the difference of two squares formula. This expression here we call the sum of two squares because it involves two perfect squares with a plus sign in the middle. The sum of two squares cannot be factored. So since this cannot be factored any further, we'll just carry it down to our final answer. So this is our final fully factored answer. So if you're using the difference of two squares formula, when you arrive at your answer, check each factor. Make sure that you don't spot the difference of two squares within one of the factors in your answer. If you do, like we saw here, you'll have to use the difference of two squares formula again to factor that expression. Let's take a look at an example of a different type of problem. The first step in any factoring problem is always to check for a greatest common factor. The greatest common factor here would be 2. So now we need to factor out the greatest common factor. We put the 2 outside of parentheses. Then we need to ask ourselves, 2 times what will give us 54p to the 6th? Well, 54 divided by 2 gives us 27. So 2 times 27p to the 6th will give us 54p to the 6th. Then 2 times negative q cubed will give us negative 2q cubed. Now that we've factored out the GCF, don't look at the original problem anymore. For the rest of the problem, we focus on this expression here with the GCF factored out, and we'll of course need to include the GCF in our final answer, but we can ignore the GCF for the time being. Let's focus on this expression here. What strategy do we need to use to factor this expression? To figure that out, we need to count the number of terms. We have 2 terms. To factor expressions involving 2 terms, we follow the instructions in this purple box here. Now, we have to decide which of the 4 formulas do we use. To help us decide, we need to determine, are we dealing with perfect squares or are we dealing with perfect cubes? This q cubed is a big hint that we're probably dealing with perfect cubes here. P to the 6th is also a perfect cube, and so is 27. So it looks like we're dealing with perfect cubes, and there's a minus sign in the middle. So since we're dealing with perfect cubes, we need to use the formula for either the difference of 2 cubes or the sum of 2 cubes. Since we said that there's a minus sign in the middle, we want to use the formula for the difference of 2 cubes. So here's the formula that we want to use right here. We just need to determine our a and our b so that we can plug those values into this formula. To determine a, we want to rewrite 27p to the 6th as some quantity cubed. To get 27, we'd have to cube 3, and to get p to the 6th, we'd have to cube p squared. Because remember, when you raise an exponent to an exponent, you multiply, so 2 times 3 gives us 6. Then to determine b, we need to rewrite q cubed as some quantity cubed. Well, to get q cubed, we just have to cube q. Now what's inside these parentheses here is our a and our b. A is 3p squared and b is q. Now that we've determined our a and our b, I'm going to copy down that formula from the previous page. This is the formula that we use for the difference of 2 cubes. And wherever we see a, we'll plug in 3p squared, and wherever we see b, we'll plug in q. So we'll plug 3p squared in for a and q for b. Then we need to square a, so we'll take 3p squared. And to make sure that we're squaring all of a, in other words, to make sure we square the whole 3p squared, we need to put it in parentheses and then square it. Then we need to add a times b, so we'll take 3p squared times q, and then we need to add b squared, so we will add q squared. Now we're almost finished, but we can simplify this expression here. So I'm going to start by copying this down since it's already simplified. Then we can square the 3 to get 9, and if we square p squared, we want to multiply the exponents. 2 times 2 will give us p to the 4th, and then we'll bring down the 3p squared q and the plus q squared. Then be very careful, after all of this hard work, our answer is still incomplete because we have to make sure to include the GCF in our final answer. So let's write this GCF out front. Let's take a look at example 4. The first step in any factoring problem is always to check for a greatest common factor. Notice here the first term, the term with the highest exponent, is negative. When that's the case, our GCF has to be negative. So I'm going to put a negative here so I don't forget. Then 2 is the largest number that multiplies into all 4 of these coefficients. So we'll put a 2 in our GCF. And y multiplies into all 4 of these terms. So we'll put a y in our GCF. Now we need to factor out the GCF. So we'll put the negative 2y outside of parentheses. Negative 2y times y cubed will give us negative 2y to the 4th. Remember, when you multiply variables, you add their exponents. So 1 plus 3 gives us 4. Now, what do we need to multiply negative 2y by to get negative 4y cubed? Negative 2 times a positive 2 will give us our negative 4, and y times y squared will give us y cubed. Then what do we need to multiply negative 2y by to get 32y squared? Negative 2 times negative 16 will give us positive 32, and y times y will give us y squared. Lastly, what do we need to multiply negative 2y by to get 64y? Well, 64 divided by negative 2 gives us negative 32. So negative 2y times negative 32 will give us a positive 64y. Now that we've factored out the GCF, we don't need to look at the original problem anymore. We're going to focus on this expression here with the GCF factored out. And we need to make sure to include the GCF in our final answer, but for the time being, we can ignore the GCF and focus on this expression here. The next step is to count the number of terms, because that will tell us which strategy to use. Here we have 1, 2, 3, 4 terms. If we look back at the first page, for problems involving 4 terms, we look at this box down here. And for problems involving 4 terms, we factor by grouping. So again, we're going to ignore the GCF for the time being and focus on this expression here. Let's group the first 2 terms together and the last 2 terms together. We'll start by focusing on these first 2 terms. Now we need to factor out the GCF of these 2 terms. The greatest common factor between y cubed and 2y squared would be y squared. So we'll put the y squared, the GCF, outside of parentheses, and then let's see. Y squared times y will give us y cubed, and y squared times a positive 2 will give us our positive 2y squared. So now we've factored the GCF out of these first 2 terms. Next, we need to factor the GCF out of these last 2 terms. Notice when we focus on these last 2 terms, the first term is negative, so that means our GCF must be negative, and the largest number that multiplies into both 16 and 32 is 16. So our GCF is negative 16. So we'll factor out the GCF. Negative 16 times y will give us negative 16y, and negative 16 times a positive 2 will give us negative 32. So we've now factored the GCF out of these last 2 terms. Now, I like factoring by grouping because you can check your work along the way. You'll know you're on the right track if these 2 factors match. So to write our answer, we can start by writing this matching factor down once, and then in the next factor, we insert these outliers, y squared and minus 16. Now be careful we're not finished because we have to make sure to include the GCF in our final answer. Now, is this answer fully factored? Be careful, because there's one thing that commonly sneaks up in your answer. The difference of 2 squares tends to sneak up in your answers. You want to check all of your final answers to see if you see the difference of 2 squares anywhere. So this is not fully factored because we have the difference of 2 squares right here. We have 2 perfect squares with a minus sign in the middle. So we need to factor this difference of 2 squares. The formula for the difference of 2 squares is a minus b times a plus b. So we have to find our a and our b and plug it into this formula. To find a, we need to write this first term as some quantity squared. Y squared can be written as y squared. To find b, we need to rewrite 16 as some quantity squared. 16 can be written as 4 squared. So a is y and b is 4. So to factor this difference of 2 squares, we'll use this formula here. We'll start by drawing our parentheses, and we'll put a minus sign in one parenthesis and a plus sign in the other. Then we want a minus b, so we'll take y minus 4, and then a plus b, so we'll take y plus 4. So we've factored this difference of 2 squares using the formula right here. These 2 factors cannot be factored any further, so we just want to bring them down for our final answer. So here we have our final fully factored answer. Let's take a look at 2 last types of factoring problems. Now this is a special type of problem here. We saw this type of problem in our 4.5 video. Notice we have a trinomial here. It has three terms. And notice this trinomial involves two variables. All of the trinomials involving two variables that we've seen is set up in a very specific way. The extra variable is attached to the middle term and squared on the constant. So in this case, the extra variable is the b. What I recommend when you see a trinomial involving two variables, before you start factoring, start by ignoring that extra variable. So we're going to ignore the b's at first here. In fact, I'm going to rewrite this problem without the b's. I've just excluded the b's because it's a lot easier to factor without that extra variable, and we can insert that variable back into our final answer. Now we want to factor this expression. The first step when you start the process of factoring is to check for a greatest common factor. There is no number other than 1 that multiplies evenly into 18, 9, and 20, so there is no greatest common factor here. Next, we have to decide what strategy we use to factor this. To help us decide, we need to count the number of terms. This problem involves 1, 2, 3 terms. So for problems involving 3 terms, we follow the instructions in this green box here. For these types of problems, you have to decide if the coefficient of your squared term is 1 or if the coefficient of your squared term is not 1. For the problem that we're working on, the coefficient of the squared term is not 1, so we're going to follow these steps here. We can see here the coefficient of our squared term is 18. It is not 1. So after you've checked for a GCF, we now need to find two numbers that multiply to give us a times c, which is 18 times negative 20, which gives us negative 360. And we need our two numbers to add to give us the coefficient of this middle term, which is negative 9. Now this is a pretty big number here, so if you're having any trouble coming up with the answer, I recommend that you list all of the factors of 360. And even though this is negative 360, we're going to list the factors of positive 360. These are all of the numbers that multiply to give us 360. For example, 1 times 360 gives us 360, 2 times 180 equals 360, etc. Now, since we need our numbers to multiply to give us negative 360, one of the numbers in each pair will have to be negative and the other will have to be positive, because a negative times a positive will give us a negative. So keeping in mind that one number in each pair must be negative, which of these pairs also adds to give us negative 9? That would be 15 and 24, because 15 times negative 24 gives us negative 360, and 15 plus negative 24 gives us negative 9. Now let's look back at problem 1 for just a minute. When the coefficient of your squared term is a 1, once you find these numbers, all you have to do is plug them into the parentheses and you've got your final answer. When the coefficient of the squared term is not 1, once you find these two numbers, you can't just plug them into the parentheses and be done. When the coefficient of your squared term is not 1, we learned in my chapter 4.5 video 3 different methods you can use. We learned that you can factor by grouping, or use the box method, or use the factor and divide method. You can use whichever method you prefer, but I really like the factor and divide method, so that's what I'm going to use. For the factor and divide method, we start by drawing our parentheses. Since this is 18a squared, we put an 18a and an 18a in the first position in each parenthesis. If this, for example, was a 6a squared, then we'd put a 6a and a 6a. Then we insert these green numbers into the blanks, so we'll put a plus 15 into one of the blanks and a minus 24 into the other. Now, this is not the correct factoring, because we should be able to FOIL this out and get this expression here. But you can see if you were to FOIL, 18a times 18a will not give us 18a squared. So we need to fix something here. That's why we call this method the factor and divide method, because after you factor, you then need to divide. So we examine each parenthesis separately, and we divide each parenthesis by its GCF. Let's examine this first parenthesis. The GCF between 18a and 15 is 3. So we're going to divide this parenthesis by the GCF 3. Then let's examine the next parenthesis. The GCF between 18a and 24 is 6. So we're going to divide this parenthesis by its GCF 6. Now we can write our final answer. Let's divide each term here by 3. 18a divided by 3 gives us 6a, and 15 divided by 3 gives us a positive 5. And then we'll divide each term here by 6. 18a divided by 6 gives us 3a, and negative 24 divided by 6 gives us negative 4. We're not finished yet. There wasn't a GCF, so we don't need to worry about putting the GCF out front. But if you were to check your work and to FOIL this, you would not get the original problem. Because remember, the original problem involved two variables, a and b. We ignored the b's at first because it was easier to factor without the b's, but then we have to remember to insert the b into our final answer. And for these types of problems, you always insert that extra variable next to the second number in each parenthesis. So we'll insert a b here and here. That will give us this for our final answer. Let's take a look at one last type of factoring problem. Now, this factoring problem doesn't quite seem to fit the mold of any of the types of factoring problems we've talked about. Let's start by checking for a GCF. Examine the coefficients here, 8, 2, and 1. There's no number other than 1 that multiplies into these coefficients, so there is no GCF. Now we need to count the number of terms. Terms are quantities that are separated by addition or subtraction symbols, and those addition or subtraction symbols should not be inside parentheses. So this addition symbol and this subtraction symbol, neither of them are inside parentheses, so these both are separating our terms. So we have one term here, a second term, and a third term. This problem involves 3 terms. For problems involving 3 terms, we follow the instructions in this green box here. But our problem looks more complicated. Typically for problems involving 3 terms, we have an x squared term, an x in the middle, and a constant. Here again, we have an x squared, an x in the middle, and a constant. Here, instead of having an x squared, we have a whole quantity being squared. And here, instead of having an x in the middle, we have a whole quantity in the middle. So for this type of problem, we want to use what we call substitution. When using substitution, find this middle quantity here. And we're going to let u equal this middle quantity. So we'll let u equal the quantity z plus 1. Notice that quantity also appears here as well. Now we want to rewrite this original problem, but wherever we see z plus 1, we're going to replace it with u. We'll start with 8. Then we'll replace this z plus 1 with u. So this quantity needs to be squared, so we need to square the u. Then we'll write plus 2. Then we're replacing z plus 1 with u. And then we'll write minus 1. The reason we use substitution is because it makes our problem look much simpler. This is the type of trinomial that we're comfortable solving. We have a variable squared, and then we have that variable in the middle. Now we can proceed to factor. We already checked for a GCF. There's no number other than 1 that multiplies into 8, 2, and 1. So when you're factoring a trinomial, after you've checked for a GCF, the next step is we need to find 2 numbers that multiply to give us a times c, which is 8 times negative 1, which gives us negative 8. And we need those same 2 numbers to add to give us this middle coefficient here, which is 2. The 2 numbers that work are 4 and negative 2, because 4 times negative 2 gives us negative 8, and 4 plus negative 2 gives us 2. Now, if the coefficient of the squared term was 1, we could just insert these numbers in the parentheses and we'd be done. But the coefficient of the squared term is not 1. When that's the case, we've learned 3 different methods that you can use. You can factor by grouping, or use the box method, or use the factor and divide method. I prefer the factor and divide method, so that's what I'm going to use. When we use the factor and divide method, we start by drawing our parentheses. Since this is an 8u squared, we'll put an 8u and an 8u in each parenthesis. Then we'll insert these green numbers in the blanks, so we'll put a positive 4 in one parenthesis and a negative 2 in the other. Now, this is not factored correctly, because if you FOIL this out, you will not get this expression here. That's because we have to factor and then we have to divide. So we examine each parenthesis and divide by that parenthesis GCF. The GCF between 8u and 4 is 4, so we need to divide this parenthesis by 4. The GCF between 8u and 2 is 2, so we need to divide this parenthesis by 2. Let's see what that leaves us with. 8u divided by 4 gives us 2u, and 4 divided by 4 gives us a positive 1. Then 8u divided by 2 gives us 4u, and negative 2 divided by 2 gives us negative 1. Now, there's no GCF, so we don't need to worry about putting the GCF out front. But we are not finished. Our original problem did not have u's in it. So our final answer should not have u's in it. Remember that we defined u to be equal to z plus 1. We used substitution here because this is a lot easier to factor than this original problem. But for our final answer, we have to make sure to replace these u's with the quantity z plus 1. So I've rewritten this exact problem, but where I see u, I replaced it with z plus 1. So I replaced this u with z plus 1, and I've replaced this u with z plus 1. Now we're almost finished. We just need to simplify this to get to our final answer. To simplify, let's distribute this 2. 2 times z will give us 2z. 2 times 1 will give us a positive 2, and then we'll bring down the plus 1. Then we'll distribute the 4. 4 times z will give us 4z, and 4 times 1 will give us a positive 4. And then we'll bring down the minus 1. Now, let's add the 2 plus 1 to give us 2z plus 3. And we'll take 4 minus 1 to leave us with 4z plus 3. And this is our final fully factored answer.